So in your last set of notes, you learned that if you can write an expression for the area of a cross-section, like the face of a cross-section of a slice of a solid, then you can integrate over the appropriate interval area times thickness of slice, where that thickness of slice goes towards 0. So is your dx or your dy or your dh, like it was in your lab report. Then you can write an integral for the volume of a solid, and we can evaluate that integral. So another way that this problem comes up, another kind of solid that we're going to consider, is this what we call a solid of revolution. Imagine you had some area in the xy plane, and you've been told you're going to revolve it around an axis. So for some people this can be hard to visualize. Feel free to come into class and try using the Play-Doh to test it out. I hope that the method I described below is helpful for sort of seeing why the integral we're going to write is correct. So just know that this idea of revolving around an axis gives just a special case of what we did in your last notes. Every time we take a slice, because we're going to slice perpendicular to that axis of revolution, the face of the slice, if I look at the slice, it's going to be a circle, and I know the area of a circle, so essentially every slice is like a very thin cylinder, and you're going to have sort of the same expression that you wrote in your lab report, the integral of pi r squared times a very small change in the thickness. So to get us started, you'll see there's some similarities to one of the problems you did in that lab report. Imagine I had this region, which I'm going to call y equals the square root of x, and I'm going to take the region between 0 and 4, and I'm going to revolve it around the x-axis. So some things to think about. We'll talk about complications later. Notice that this region bumps all the way up against the axis of revolution. So this is completely connected. There's no space between my blue region and my red line, which I drew in the x-axis. Remember, the x-axis has the equation y equals 0. So when I revolve that around, I'm going to get this shape. You can see I've made it here. It kind of looks like a bowl. The technical term is a paraboloid. And that's because if you flip this up, it would look like y equals x squared, and that's a parabola. And if you took it and spun it around so it forms a solid, we call that a paraboloid. And we can use that same technique that you worked on in class today to write an expression for the volume of this. And since we already know this example, it's going to sort of set the stage. We'll talk about a list of steps you can always use to find the volume of a solid of revolution. All right, so these are steps I like to use. I'm going to suggest a color coding scheme, so feel free to revise it or use your own. But I find this to be helpful because when I see this picture, I have a better understanding of what a slice looks like, which gives me a better chance of writing the correct integral. So that green line I can think of as this green segment here, I can kind of think of as a radius. And then when I see the whole picture and I draw this sort of circle, very thin cylinder in, then I can get a better idea of what my slice looks like, and I can make sure that I'm using the right variable for the thickness, and that helps me. So I'm going to show you how I make that picture, and I hope it's helpful to you. All right, so I made this picture bigger, and that made the list of steps fall off, but we're still going to follow those same steps. So the first step I recommend is you shade in the region that they say you're going to revolve. So here, it's region R, then it's been suggested I revolve around the x-axis, and I notice that it's helpful if that shading isn't too dark. So I've used a nice light gray, and I've shaded in region R. So then I'm going to draw the axis of revolution. I've been asked to revolve this around the x-axis, so I suggest drawing that in red. You can see in both of my pictures I've already drawn that in red. And then I'm going to draw the region I shaded. I'm going to pretend I reflect it over that radius. So I'm going to, reflect is the fancy way to say make the mirror image, right? So there's my mirror image. if I'm joking around, I might call that R to show it's a reflection of R. So now I have my picture, and you can see how that picture that I've drawn in gray can, for some people who are ready, lead you to sort of this visualization. That's the shaded brown picture on the right-hand side. So now that I have my original region in, if it's helpful, I know this is y equals square root of x, and I know that goes from 0 to 4 along the x-axis. My suggestion now is to draw in a slice. So that picture I just showed a second ago with the green slice, I'm going to try to make that picture. I'm going to change my pen to green, and here's what I say. Start at the axis of revolution. I'm going to put my pen on the axis of revolution, that's the red line. And I'm going to draw toward the far edge of the shaded region. So I'm going to draw toward the far edge of R, not the reflection of R, but try to draw toward the far edge of R. And then pretend I'm drawing all the way back around behind, you can't see my finger. So start at on the radius, draw toward the far edge of R. For me, in this case, I'm gonna have to go up because my R is above my axis. I'm gonna pretend I'm drawing back behind the red revolution line and back up to where I started. So this is me. I'm drawing one slice. I start at the axis of revolution. I draw toward the far edge of R, back behind the axis of revolution, and come back to where I started. Now, obviously the picture I showed you has a much nicer looking slice. But if you get to the place where this picture you can draw leads you to that visualization of what we had, you're going to be in really good shape. Okay, so that was step 4. Notice at the end of step 4, I've in italics, probably should have put this in italics in lots of other places too. In high school calculus, the only methods we'll talk about for finding the volume of a solid include taking slices, whatever that means, perpendicular to the axis of revolution. So that's for volumes of solids that come from revolving around an axis. The only way we're going to talk about finding those volumes is pretending we're taking slices that are perpendicular to that axis. So I was revolving around the x-axis, which is horizontal, which means my slice has to be vertical. Now there's other ways to find volume. They do not come up in high school calculus. So if this is helpful to you to always focus on taking your slices perpendicular, I find that that helps most students. Okay, so step 5, I'm going to use my blue marker. I'm going to try to draw in a radius of my green disk. So I'm going to start at the axis of revolution. So if I pretended that green disk, like it's a circle with thickness, so I'm going to find the center of the circle. That's going to be on the red line, right? And I'm going to draw toward the function in the picture. It has to be in the shaded part. Don't try to draw toward the reflection, because it's in the shaded part where I have an equation for the boundary, and that's what I'm going to need, is an equation to bump into. So I'm going to start my blue line at the center of the circle, which is one face of my disk, and I'm going to draw toward the edge of the green disk. That wasn't especially centered. Let me try one more time. There we go. It's that blue line segment that I need an equation for. If I have this picture, it's much easier to try to draw that, to write that equation, than if I don't have the picture. Okay, so part 6 says use horizontal or vertical distances to write an expression for the blue radius of your green slice. So my blue radius, it's a vertical line segment, which means if I wanted to find out how tall it was, I would subtract the top y minus the bottom y, because the 2 points at the top and the bottom of that blue radius, they have the same x, so the x's don't figure into the distance of that blue line segment. So top minus bottom, essentially, and notice what function I bumped into on the top was square root of x. What function did I bump into below? Well, that was my axis of revolution, which is the x-axis. Remember, the equation for the x-axis is y equals 0. So that's an expression for the length of that radius. Now, maybe you don't want to write the minus 0. You can tell that that just simplifies to square root of x. That's good. Maybe I'm foreshadowing something that comes later. And then you have a step 7. Okay, so sum the volumes of all the slices by integrating. This is what we learned back in the last set of notes, which is I'm going to integrate area times thickness. So I needed a radius because in this case, in all the cases in this set of notes, the slice is going to be a very short, a very thin cylinder. So I'm going to need to write the volume pi r squared times thickness. I'm going to write an integral. The thickness of my slice, the thickness of that green disc, is a very small change in x. So that helps me to see. I've had to take slices that are perpendicular to the x-axis. That means the thickness of the slice is a very small change in x. So I'm going to write dx here, which tells me I'm going to have to put x limits on my integral. Well, region R covered x values from 0 to 4. This is going to be pi r squared. Area of a circle in this case. So pi, what am I going to use for r? I'm going to use this expression I wrote here. I'm just going to simplify it to radical x. But if you put radical x minus 0, you still get it, right? Okay, so now I have an integral that I can use to evaluate the volume of that solid.